Okay, so welcome back. So here's where we are in the schedule. All right. So today, it's good. It's good I do this because it's good to remember what day it is, right? But today is Wednesday, October 14th. It's day 17. I'm labeling my videos according to day number, right? I'm building off of the spring videos. We're going to finish part 3 of the course today. It's very dense material. I have 83 minutes of video, so no time to dilly-dally. Lessons 19 through 23, part 3 of the class. This will all be due next week, Thursday, October 22nd. Okay, that's the due date for part 3 of the class. All right. Now, next week is going to be homework sessions, right? That's going to be next week. And then the homework's due that Thursday. Friday, October 23rd, Friday of next week, is withdrawal deadline. If you drop before then, you get a W. If you drop after, you get a grade. And speaking of which, the homework 1, I will definitely get graded by next week, okay? Because obviously, I would like to have something graded by the withdrawal deadline. So definitely homework 1 will be graded next week. I'll email you with results. All right, any questions before we start the main videos? Because lots of stuff, 83 minutes of videos, lots of stuff. Go ahead and put questions in chat. All right, let's begin. Let's begin, all right?
Hi, everyone. We're continuing our discussion of the central limit theorem, the CLT, for sums, but more importantly, for means or averages. Okay, in the beginning, we talked about this probability distribution for rolling one die. It was a discrete uniform distribution, which for now we'll call Big Daddy D. Probability is 1/6 for each face from 1 through 6. Now, from either zigzagging or because this was discrete uniform, we can add these up and divide by 6. We can find the mean of this distribution, 3.5. Now, taken on faith that the standard deviation was about 1.7. To be safe, I'm writing this to 5 sig figs. If you're curious about the calculation, look back at the optional handwritten notes from lesson 16. Now let's say we wanted to do a spike plot for the probability distribution here for one die. N equals 1. We have 1/6 probability mass at the face 1, 1/6 at 2, and so forth, all the way up through 6. Discrete uniform, we have a flat top. But what if instead of one die, we consider 2 dice? Now, 2 dice, we have a result on a red die and a result on the green die. I know in Vegas, we tend to care about the sum, but for our theory here, we're going to look at the average of the 2 dice, X bar, the sample mean. When we roll 2 dice, we're taking a sample of size 2 from this Big Daddy flat distribution. What's the probability distribution for X bar? It's also called a sampling distribution in the sense that if we have, say, 1 million students providing 1 million samples of size 2, then when we do a relative frequency histogram or spike plot, it should look something like this. It will be triangular, very close to this triangle. Now, what are some similarities and differences? Now, the center, the mean of the mean distribution, is still 3.5, just as the center was 3.5 here. Bear in mind that if you're rolling one die, the average on the die is the same as the die result. X bar equals X, basically. But notice that the 3.5 is still the center, whether it's here or here. And in fact, as n increases, the center will always be 3.5. The mean of the X bar distribution will always be 3.5 if you're starting with this Big Daddy distribution. So that's the same, the mean. What's different is the standard deviation or the standard error for the mean. The standard deviation of the X bar distribution is going to be less because we're getting greater clustering, a tighter clustering about the mean 3.5 than over here. Here, things were more spread out. Let's go on. And by the way, as we go on to 4 dice, 8 dice, and so on, what kind of shape are we going to approach? More and more, we're going to approach a normal shape, a bell shape. N equals 4. Tighter clustering around 3.5 for the sample mean, more bell-shaped. N equals 8. Tighter clustering, more bell-shaped. N equals 16. Even tighter clustering, even more bell-shaped. N equals 32. Even tighter clustering, about 3.5, very little spread, and very bell-shaped. In fact, it's official. Once n gets past 30, we can say officially that we can approximate this with a normal distribution. It'll be this over here. And we explained this distribution last time. Rolling 32 dice. Now, the central limit theorem applied in this case because n, 32, the sample size, was greater than 30. Okay, that told us that we can expect a bell shape here. But it turns out that if we had started with the bell shape way back here, if the original Big Daddy distribution were basically normal, then we'd have normals throughout, and the sample size wouldn't matter so much in terms of our ability to apply the CLT. In this case, with dice, we have to rely on a large sample size. But if we start with a normal distribution at the outset, then the sample size doesn't matter in the sense that we can still apply the CLT, whether n is bigger than 30 or not. The 30 does not come from formulas or algebra. It's just from practical observation. Pure mathematicians don't like that. Okay, so according to the CLT for means, if a machine rolls 32 dice, imagine all these 32 Crayola colors on the dice, then the sampling distribution, or probability distribution for x bar, is approximately normal. The mean of this distribution, denoted mu sub x bar, is in fact the same as the Big Daddy mean, 3.5, as it always was, for 1 die, 2 dice, and so forth. The centering is always about 3.5, Big Daddy mu. But the standard deviation for the x bar distribution, the standard error, was not Big Daddy sigma. It was not the 1.7. It was this number divided by the square root of n, the sample size, the square root of 32. This fraction is about 0.3. Again, I like to write this to 5 sig figs. So the standard error is about 0.3, way less than the 1.7 we had for 1 die. For 1 die, very spread out, standard D was about 1.7. By the time you get to n equals 32, you're down to 0.3. And a bell shape, by the way. Okay. Remember, the standard dev is the distance between the mean line and either inflection point. And we're focusing on x bar, this row, because we're looking at the sample means, not so much the sums. Greater, tighter clustering around 3.5. That means less spread, a lower standard error, or standard dev, for the x bar distribution. So this is our normal approximation for the distribution of x bar. Let's apply these ideas. So first of all, we can talk about the idea of usual values for a sample mean. So let's say that we have a machine that rolls 32 dice, standard dice. And you might be taking bets on what the average will be for these 32 dice. Well, what would we expect? So if the machine rolls 32 dice, what would be typical usual values for the average of those 32 dice? For example, would 1.3 be a usual value? Could 4.9 be a usual value? We know the average values have to be between 1 and 6, but which of those values would be usual? Sort of typical for this machine that rolls 32 dice. Okay, in lesson 9, we talked about the 2 standard dev, the 2 sigma rule for usual values. The idea that the range of usual values will be within 2 standard devs of the mean. That was the idea of the 2 sigma rule. We can now extend this to the 2 SE rule, the 2 standard error rule, where we have 2 times sigma sub x bar, 2 times the standard dev of the x bar distribution for usual values of a sample mean. We're analyzing means, remember. A machine is rolling 32 dice, and we're taking bets on what the mean will be. The 2SE rule for usual values of a sample mean. An appropriate interval of usual or typical values for a sample mean is given by this. The mean minus twice the standard error, comma, mu plus twice the standard error. Basically values within 2 standard errors of the mean, mu. Here's an example. An interval of usual values for a sample mean where we have a machine rolling 32 dice. A machine rolls 32 standard 6-sided dice. What is the interval of usual values of the sample mean on those dice, x bar, based on the 2SE rule? Right now, it's a random variable. The dice have not been rolled yet. I don't know their values yet. But I do have an idea of its distribution. That's from the central limit theorem. Well, the central limit theorem told us that the distribution for x bar, the sample mean, can be approximated by this normal distribution, with mean 3.5 and standard deviation or standard error 0.3, roughly. I had it to 5 sig figs before, but let's just say it's 0.3 for now. So based on this approximation for the distribution of x bar, what are the usual values? What can we expect that the machine will roll as an average value? All right. What's mu minus twice the standard error? The mean was 3.5. We subtract twice the standard error, 0.3. We end up with 2.9. So that's on the low end of usual values. What about the higher end? Mu plus twice the standard error, 3.5 plus twice 0.3. That ends up being about 4.1. That's like an upper limit for usual values. So the interval of usual values of the sample mean is given by this interval from 2.9 to 4.1. If we have a machine that rolls 32 dice, then we're pretty sure that the average of those 32 dice will be between 2.9 and 4.1. So you probably wouldn't want to bet on something like 1.3 or 1.4. In fact, you shouldn't bet on any particular number. You'd want to bet on a range or an interval of values. Well, if you can bet on a range this wide, bet on this, 2.9 to 4.1. All right. Now, since x bar has an approximately normal distribution, we can apply the empirical rule, 68, 95, 99.7%. Remember, the empirical rule said that we're going to have about 95% within 2 standard deviations or 2 standard errors of the mean. So we can say that the probability that the sample mean will be between 2.9 and 4.1, that's within 2 standard errors of the mean, that's going to be about 95% or 0.95. So we're pretty sure that when the machine rolls the 32 dice, the average will be between 2.9 and 4.1, because the probability will be about 95% of that happening. It's not likely to be below 2.9 or above 4.1. Of course, 3.5, we would expect values about 3.5. All right. Let's say we want to do more with probabilities. Let's say that we want to compute probabilities more accurately. When finding probabilities for the sample mean, x bar, we need to adapt our formula for z-scores. Formula for z-scores for sample means. Now, old school, you remember from previous lessons that a z-score is obtained by taking a value of interest, like a boundary value, subtracting off the mean of the corresponding distribution, and then dividing by the standard deviation, or in this case, the standard error. Now here, we're going to plug in values for x bar. We're taking bets regarding the average of the 32 dice. So we're interested in values for x bar. To use this formula to find a z-score, we have to subtract the mean of the x bar distribution and divide by the standard deviation of the x bar distribution. Again, this is known as the standard error, maybe to distinguish it from the standard deviation of the Big Daddy distribution, sigma. All right. The formula is ultimately this, and then we'll round off to 2 decimal places. We take the x bar value of interest. Like you're taking a bet. You're betting that the average will be between this value and that value. Okay, x bar is like a boundary value of interest. We subtract off the mean of the x bar distribution, but wait, according to the CLT, mu sub x bar is the same as the Big Daddy mean, mu. Sigma sub x bar, however, is not just Big Daddy sigma. It's sigma over the square root of n. So this is ultimately the z-score formula you want to plug into. An example. Example 2.
I want to make a comment. I believe in the next example, I actually use the formula over here, but many students just plug in numbers directly into the final formula here. But you have your choice. Here I kind of separate it out. If you think more in terms of theory, I kind of build it up this way.
Probabilities for a sample mean when we roll 32 dice, or hopefully a machine is doing it for us. A machine rolls 32 standard 6-sided dice. The distribution for X, the result on one die, this is the distribution Big Daddy D, right? The mean for Big Daddy D is mu equals 3.5. The standard dev, Big Daddy sigma, is about 1.7. To 5 sig figs, it's that. That was the original distribution for one die. The question here is, let's say that you bet that the average of the 32 dice that the machine rolls will end up having an average between 3.0 and 4.0. Now, bear in mind, since we're talking about normal approximations, normals are continuous distributions, we don't care so much whether there are bars here or not, because the probability of getting these boundary values is so close to 0. In fact, it is 0 for continuous distributions, the normal approximation. But let's say you bet that when the machine rolls the 32 dice, the average on the 32 dice will be between 3.0 and 4.0. Find the probability that the average of the 32 dice, x bar is the average, will be between 3.0 and 4.0. We want to find this probability using the normal approximation afforded to us by the CLT for sample means. All right. Now, as we do our work, we're going to need these hints from the Z distribution, and you can find this from software like tutorhomework.com or Excel maybe, but take these hints on faith. These are hints that I got from Excel, let's say. We'll use these later. But we're going to need this information to work out this problem. So how do we start? We're going to start by finding the Z-scores for these boundary values. The 3.0, whoops, the 3.0, and the 4.0. I need to find Z-scores for these boundary values. I need to standardize these values so I can use the Z distribution and these hints. That's our first step. Well, actually, the first step may be, oh yes, the CLT applies because the sample size is big enough. N equals 32, the CLT applies. You could say that's really the first step. Okay. But we talked about that before. We talked before that the sampling or probability distribution for X bar, when we roll 32 dice, okay, has approximately a normal distribution with mean 3.5, the same as the Big Daddy mean, mu, and standard error, that's the standard D for the X bar distribution, about 0.3. Sigma over root n, that's about 0.3. We're going to use this normal approximation, it's a normal distribution, and we're going to calculate based on this normal distribution. All right. Find the probability that X bar, the sample mean, is between 3.0 and 4.0, assuming that this is basically the distribution for X bar, this normal. Again, we're going to take the boundary scores, the 3.0 and the 4.0, and convert them into Z-scores so that we can use the hints. For X bar equals 3.0, Z equals, now you could plug directly into what I showed you earlier, this over here, but I calculated the standard error for you. Sigma over root n was about 0.3. In fact, I had it to 5 sig figs. So I'm going to use this instead, more generically. Okay, so the boundary value of interest, 3.0, the value for X bar, we subtract off the mean of that distribution, 3.5, same as Big Daddy mu, all over the standard error, that's the 0.3 thing. Okay, work this out, it's about negative 1.66. Why does it make sense that this is negative? Why does it make sense that this Z-score is negative? Well, what is the mean of the X-bar distribution? It's 3.5. What number are we looking at here? Converting, 3.0. How does 3.0 compare to 3.5? 3.0 is less than 3.5, so that z-score better be negative. Okay, what's the z-score for 4.0? If you work it out, it turns out to be positive 1.66. Now, instead of working it out, you could just use symmetry, because I'll use a different color here. Here's 3.5. The mean for both the X-bar distribution and the original Big Daddy D distribution. 3.0, let's say, is over here. 4.0 is going to be over here. 4.0 and 3.0 are symmetric about 3.5. So if the z-score for 3.0 is negative 1.66, then the z-score for 4.0 has to be positive 1.66. If 3.0 is 1.66 standard deviations below 3.5, then 4.0 is about 1.6 standard deviations above 3.5. You can use symmetry. Bear in mind, if we had instead 4.3 or 4.5, then we could not use symmetry. We'd have to work this out again, putting a different value here. In this case, we can use symmetry to get this. All right. What's the corresponding probability expression for z? Okay, the probability that, I apologize, there should be x bar here. The probability that x bar, the sample mean, is between 3.0 and 4.0, that's going to be about the probability that z, a standard normal z, is between negative 1.66 and positive 1.66. How do we do these in-between probabilities? Okay, well, we need the probability to the left of positive 1.66, that's going to be big, 0.9515, that's all of this to the left of 1.66. And we subtract off the probability to the left of negative 1.66, that's small, 0.0485, that's this piece over here. That's the piece we subtract off. Remember, where did I get these probabilities or areas? They were from the hints over here. To the left of 1.66, we had a probability or area of about 0.9515. Over here, to the left of negative 1.66, we had a probability or area of about 0.0485. By symmetry, these are complements. Notice that this area here is the same as this area over here. That's by symmetry. Anyway, from these hints, we subtract these two probabilities. Again, 0.9515 to the left of the bigger number over here. We subtract off the smaller probability, the 0.0485 to the left of negative 1.66. That's this guy over here. We subtract in order, greater minus smaller. Of course, because probabilities are never negative, right? The answer, I'll put this in red. The answer is 0.9030, which means that if you're betting that when the machine rolls the 32 dice, the average will be between 3.0 and 4.0, you're probably going to win that bet. With over a 90% probability, you're going to win that bet, that the average on the 32 dice will be between 3.0 and 4.0. Again, the probability of something like getting 32 threes or 32 fours, the probability of something like that happening is so minuscule, we don't worry about that. Even if the average overall is exactly 3.0 or 4.0, we don't worry about that. All right, probability is about 0.9030. And this is for cases where the 68, 95, 99.7 rule don't apply directly. We don't have 2 standard deviations here. We have 1.66 standard deviations, so we didn't have the empirical rule useful for that. All right. One side note, in Vegas, we usually care about the sum of dice. Bear in mind, you won't have to know this for the homework. But let's say that, like Vegas, you're more interested in the sum or total of the dice. There is a CLT for sums. Now remember, in this class, we're focused much more on the CLT for means or averages, but we do have a CLT for sums. So for example, if the average on the 32 dice is between 3 and 4, then the sum of the 32 dice is between 96 and 128. Okay, so if the average of the dice is 3, the sum is 96. You multiply 3 by 32. If the average is 4, you multiply by 32, that's 128. Now again, we're saying the probability of getting exactly 96 or 128 is fairly small, so we're not going to worry about the bars so much. In fact, we won't when we do the normal approximations. Okay, again, here for 32 dice, a sum is 32 times the average. The CLT for sums implies that the distribution of the sum will be approximately normal, where the mean is n times mu. So 32 times 3.5 is 112. So that's the sum total that they'll tend to center around. The standard deviation for the sum, is sigma times root n. Basically, it's sigma over root n times n. That's about 9.7. So if you're curious about the sums, the distribution for the sum of 32 dice will be more like that, with these parameters. Again, don't worry about this for the homework. So finally, next time, we're going to look at the statement of the central limit theorem, the CLT for means. We've seen bits and pieces. We've even seen applications to examples. But what is it? What is the statement of the central limit theorem, the CLT for means? That big guy is next time.
Well, before we go to the statement, which you won't have to memorize, but any questions about these examples? Any questions about these examples? We're analyzing sample means, things like usual values and probabilities. Any questions? Any questions? Feel free to put questions in chat. Let's go on. The next one's about 9-10 minutes.
Hi, everyone. We're finishing up lesson 22 on the central limit theorem, the CLT, for means or averages. And finally, we're going to meet this theorem. We've seen them in bits and pieces. We've applied them in problems and examples. We're finally going to state the CLT for means. It's a lot. But basically, be aware of the assumptions and apply it when appropriate. The central limit theorem for means. Assume that X has some distribution D as the Big Daddy distribution. It was discrete uniform for one die. The mean is mu. The standard dev is sigma. That's the usual notation. We assume that sigma is finite, not infinite. Don't worry about that. So far, so good. The Big Daddy distribution is D, our old school notation. Mean mu, standard dev, sigma. So far, so good. Let X bar be the sample mean of n IID results from D, the Big Daddy distribution. Now, IID, these are three famous letters in probability theory. IID means independent and identically distributed. Independent in the sense that, let's say that you have a machine rolling 32 dice. The result on one die has no impact on the result of another die. They aren't magically connected by magic glue or anything. These dice are independent. And they're identically distributed. In particular, if you take each die has that flat Big Daddy distribution as the common identical distribution for all 32 dice. They all have distributions that are identical, the same distribution. Here I'm drawing a more generic picture. So of course, a die had a flat top. Here we have a more messed up distribution, but this could still work for the central limit theorem. We could have n IID results from this distribution over here. Okay, so we have this Big Daddy distribution D, and we're drawing from it a sample of size little n. So for example, let's say we have dice, so we have the flat distribution. Let's say we have dice. We have a machine roll 32 dice. X sub 1 is the result of the red die. X sub 2 will be the result of the green die, and so forth. X sub 32 is the result of the orange die, whatever. The sample mean, X bar, is going to be the average of all these. As a random variable, Basically, it's telling us that whatever these 32 values will be, we'll add them up and divide by 32. But since the dice have not yet been rolled, right now x bar is a random variable. And it has a corresponding probability distribution. We don't know the value of x bar yet, but we can approximate its probability distribution by a normal distribution because of the CLT. All right, so here's our sample. It could be like 32 dice. There's our sample. We're curious about probabilities for the sample mean. Okay, now when can we apply the sample mean? If the sample size is large, in particular, n is greater than 30. The 30 comes from practical observation, not from formulas or algebra. Or, regardless of the size of the sample size, if you start off with a normal distribution, if Big Daddy D is a normal distribution, pretend that's normal, then the CLT applies regardless of the sample size. So if the sample size is big enough, bigger than 30, or if you start off with a normal distribution, then the CLT applies. And this normal distribution can be used to approximate the distribution for the sample means. And we can work out probabilities. According to the CLT, under one or both conditions, x bar has as its distribution, approximately, a normal distribution with this mean and this standard deviation or standard error. The mean, mu sub x bar, is simply mu, the mean of the Big Daddy distribution, d. The standard error, or the standard deviation of the x bar distribution, the standard error of the mean, is given not by sigma, not the standard dev of the Big Daddy distribution, but sigma over root n. The Big Daddy standard deviation divided by the square root of n. This is going to be smaller. As n increases, as the sample size increases, the standard error shrinks, and we get tighter clustering about the mean. We saw this with the dice. Now, the CLT works best if you start off with a normal distribution. But just in general, when does the CLT tend to work better? And when do we need maybe smaller values of n as a requirement as opposed to really needing larger values of n, the sample size? In general, when does the CLT work well? Well, what are some properties of normal distributions? Well, they're symmetric, and they don't have thick tails. In fact, normals fall off very fast. That's why we have almost everything within 2 or 3 standard deviations of a mean if you have a normal distribution. So even if you don't start out with a normal distribution, generally speaking, the central limit theorem tends to work better when we have at least a roughly symmetric distribution and something where the tails fall off rapidly. So we don't have something super lumpy like this on the edges. All right, so let's see how the central limit theorem does. Before, we had a standard die with a uniform distribution. What if we have a loaded die? Or maybe you have a die like this, where 3 of the faces are 1s, 2 of the faces are 2s, and 1 of the faces is a 3. Which means that the probability of getting a 1 is 1/2. The probability of getting a 2 is 1/3. The probability of getting a 3 is 1/6. This is not a uniform distribution. And the mean is not obtained by adding these up and dividing by 3. You have to use the zigzag. This times this, plus this times this, plus this times this. The mean is about 1.7. It's biased more towards the 1 as opposed to the 3 because a 1 is much more likely than a 3. The standard dev is about 0.75. Again, we didn't cover that calculation before, but take that on faith. All right, so for one die, here's a straight up spike plot for the original Big Daddy distribution. 1/2 mass for 1, 1/3 mass for 2, 1/6 probability mass for 3. That's a spike plot for n equals 1. For n equals 2, what if we take the average of these 2 weird dice? We get this spike plot. N equals 4, n equals 8, n equals 16, n equals 32. Now, by the time we get past 30, look at this. The distribution of sample means is very normal, and there's a tight clustering about 1.67, the Big Daddy mean. And that was the case even though this was not normal, not uniform. It wasn't as good as a uniform in the sense that it's not symmetric. So unlike a normal curve and unlike the uniform distributions for the dice, this year, this is not symmetric. So we had to wait longer. We had to wait a bit longer for us to get that bell shape. Okay, before there was a marked skewness to the right. All right, and the CLT would apply. These are the new parameters. All right. And again, if you had a distribution that was very asymmetric or something that was very lumpy on the edges, then it might take a while. It might look pretty messed up for n equals 4, n equals 8, very far from normal. But even for a messed up distribution like this, by the time you got to n equals 32, the result will be fairly normal. Even for a messed up distribution like that. Actually, I apologize. It is kind of symmetric, but the problem is it's very lumpy in the tails. Right. Maybe something that's even more messed up might be something like this, where it's like maybe this here, that there, where it's asymmetric and kind of lumpy tails. Okay, so that is the central limit theorem for means. Next time, we're going to talk about another application of normal distributions, approximating our old friends, the binomials from before. And that's next time.
So the CLT for means, that's going to be the core for our inferences for means in the last part of the class. Any questions before we get to lesson 23? Again, this is one of the deeper days of the semester. Questions. Feel free to put questions in chat, all right? Let's go on to lesson 23, last lesson of the part.
Hi, everyone. Before we start lesson 23, I'd like to explain why we care about normal distributions, just in general. Well, first of all, we often see them in real life. And this is sometimes referred to as the soft central limit theorem, the idea that if you have a variable like weight or height, where there are many different sources or inputs, then they combine to form a random variable that has about a normal distribution. That's a general idea of a soft central limit theorem. It's not too precise, but it's the idea that if you have a variable that's affected by many different inputs, then it's often randomly distributed.
Normally.
Second, more precisely, sums and averages, as we've seen, are often normally distributed. Like if you have a machine roll 32 dice, and you look at the distribution of the average of those dice. In an application, you could talk about 32 weights of American adults if you're designing elevators. A third application, which we're going to do now, normal distributions can be used to approximate binomial distributions, our old friends. And let's see how. In lesson 23, normal approximations to binomial distributions. How can normal distributions help us analyze binomial distributions so we can do things like approximate probabilities? Okay, so first of all, when can a normal distribution approximate a binomial? We're going to look at a gallery of 50 binomial histograms and observe which of the histograms looks closest to normal. So here's the first part of the gallery, all right? For example, let's review binomial experiments. A classic binomial experiment is if you flip a coin, let's say a fair coin, where the probability of heads, p, is 1/2. You flip a fair coin n times. Well, if you flip a fair coin once, there's a 1/2 probability of getting a head. So there's one head, and a 1/2 probability of getting a tail. So there are no heads. Now, if the probability of getting a head is, say, 7/8, well, then there's a skew. The probability of getting one head is 7/8. The probability of getting a tail is 1/8. The 1/8 is the value of Q. Remember that Q is given by 1 minus P. It's the complementary probability. the probability of a tail. Now, if you flip two coins, or if you flip the same coin twice, well, if it's a fair coin, the probability of one head is 1/2. The probability of no heads is 1/4. The probability of two heads is 1/4. So we have these binomial histograms that can be used to graph binomial distributions. N is like the number of times you flip the coin, and P is the probability of the coin coming up heads. If P is 1/2, you have a fair coin. Otherwise, you have a biased coin. Here, the coin is biased towards heads. Over here, the coin is biased against heads and towards tails. As you see, we're more likely to get tails than heads. So if we take this up to n equals 10, which of these 50 binomial histograms looks most normal? Take another view here. Which of these 50 histograms looks most normal, looks most bell-shaped? If you guess this one, ding, 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 speaking of bells, you'd be correct. And what is this distribution? This is the binomial histogram, the binomial distribution, where n equals 10. So you flip a coin 10 times, and it's a fair coin. P equals 1/2. P equals 1/2, n equals 10. This, in fact, is the only one of the 50 histograms or distributions that can be approximated by a normal, as it turns out. This is the only one of the 50 that will be fair game. Because these other ones are too skewed, like the ones over here and over here. And even for the P equals 1/2 column, it's a bit too chunky beforehand. It's not so bell-shaped, it's too chunky. So this histogram or distribution is the closest one to bell-shaped, normal-shaped, and in fact, it's the only one of these 40 that will be permissible
50.
to be approximated by a normal distribution. Now, before we go on to the specific assumptions, let's remind ourselves what this distribution looks like. What is the distribution table for this histogram? Hi, everyone. We're going to use Excel.
Yeah, I think I made a quick cut there. So I'm going to an Excel example here.
To find the probability distribution table corresponding to this histogram. Remember, the distribution we're dealing with is a binomial distribution with parameters n equals 10 and p equals 1/2. So a classic example of this is if we're flipping a fair coin 10 times. The probability of heads is 1/2, and we have 10 trials. The most likely number of heads is what? It's 5 heads, and that's why the bar there is highest. And notice that because we have a fair coin, p equals 1/2, we have symmetry about that middle bar. So when we do the table, we should see these properties. P of 5 should be highest, and we should see symmetry about P of 5. And lo and behold, if you use Excel, that's what we get. Imagine flipping a fair coin 10 times, count as successes heads. Let X be the number of heads on the 10 flips. So here's the binomial table, where X has a binomial distribution, where n equals 10 and p equals 1/2. We have a fair coin. How many heads can we get? Anywhere between 0 and 10, integer. Notice the probability of 5 heads, p of 5, is the highest among these. It's about 25%. Notice that p of 4 is equal to p of 6, about 21%. Notice that p of 3 is equal to p of 7, about 12%. We have symmetry about p of 5. It's very unlikely you'll get no heads or all heads. And the probabilities here add up to 1. That's the sum. That must be true of any probability distribution table. All right, now let's say that you wanted to find p of 5 in particular. Well, remember, there was the old binomial formula from before. We could use Excel, find the probability that X, the number of heads, is 5, where X has that binomial distribution. The command is binom dot dist. X equals 5, that's the number of successes or heads you're looking at. N equals 10, that's the number of flips or trials. P equals 1/2, that's the probability of heads, a success. And we put false here because we want a particular probability, not a cumulative probability. If you put true, then you get a cumulative probability, meaning you get the probability that X is, say, less than or equal to 5. Then you get the sum of these probabilities here. We want individual probabilities, so we make this false. If we put that in, equals binom.dist, X equals 5, N equals 10, P equals 1/2, false. We want a particular probability. We get about 25%, the same number as over here. And again, these probabilities are seen as heights in this corresponding histogram. All right, so we know a lot about this distribution. And as I claimed before, of these 50 distributions, these 50 histograms, the only one that we counted as approximately normal was this one. And why is that? What are the assumptions under which we're going to allow a normal approximation for a binomial? When can we say that a binomial histogram looks normal? It's under these conditions. Conditions for using normal approximations to binomial distributions. We will use normal approximations to binomial distributions if and only if the following two conditions apply. If NP and NQ are both at least 5. Remember that Q is 1 minus P. It's the probability of a tail in our examples. Now, why does that make sense? Well, remember that of the 50 distributions that we saw, this was the only one that counted. The binomial, where N was 10 and P was 1/2. It was the most basic binomial distribution that can be approximated by a normal distribution. So as N gets larger, if you consider larger values of N, like N equals 100, N equals 1,000, and so forth, then more distributions, more histograms will count as normal looking. Of course, it helps to be close to 1/2 and not to be too close to 0 or 1. So, normal approximations to binomials are more appropriate if the sample size or the number of trials, N, is large, and if P is pretty close to 1/2, or at the very least, if P and Q are not too close to 0 or 1. So here's the idea. If N equals 10, you really need P equals 1/2 in order for this to count as normal. But if we were to do N equals 100 or N equals 1,000,000, then many values of P will work. Only the most extreme values of P and Q would fail us. So if N equals 1,000,000, then P and Q could be almost anything. It's just that a P and Q could not be too close to 0 and 1. And by the way, if P is too close to 0, then Q is too close to 1, and vice versa. If P is too close to 1, then Q is too close to 0. Ideally, we want values of P and Q that are close to 1/2. But the greater N is, the higher N is, the more we can deviate from 1/2, 1/2. So this here represents a compromise. Here's the idea. When are we more likely to be able to use a normal approximation to a binomial? If N is big, and if P and Q are not close to 0. Again, when are normal approximations appropriate? The larger N is, and the further away both P and Q are away from 0. So if you have these two conditions applying, if NP is at least 5, and if NQ is at least 5, then that guarantees that N is big enough and that P and Q are not too extreme, so that neither one of these is too close to 0. So under these conditions, we will say that a binomial histogram looks about normal if NP is at least 5 and if NQ is at least 5. But what is the normal approximation we're going to use? We're going to see next time.
Okay, so on the homework, if I ask, could you verify if a normal approximation is appropriate to a binomial? That's what I'm talking about. All right. Questions in chat. Questions in chat. Okay. All right. Let's go on.
Hi, everyone. We're continuing with lesson 23 on normal approximations to binomial distributions. We're saying that these normal approximations apply under these conditions when NP and NQ are at least 5, where Q is 1 minus P. N, remember, is the number of trials. P is the success probability per trial. Q is the failure probability per trial. So for example, N could be the number of flips of a coin. P is the probability of heads per flip. Q is the probability of tails per flip. Now, both these conditions favor a normal approximation because larger values of N tend to favor a normal approximation, and values of P and Q that are not close to 0 will also favor a normal approximation. So of these binomial distributions or histograms, the one that really does count is this one over here. N equals 10, P equals 1/2. This is the one binomial distribution of these 50 for which the normal approximation will apply, because NP and NQ are 5. Now, on top of these defining parameters for the binomial, N and P, we also care about the mean and standard deviation. So the mean and standard deviation are 2 more parameters for the binomial distribution that we care about, and we're also going to need those values for their normal approximations. So what are the formulas for the mean and standard dev of a binomial distribution? Well, from probability and algebra, we get that the mean mu is given by N times P, which makes sense because, for example, if you flip a fair coin 10 times, if N is 10 and P is 1/2, then the expected value is 5 heads. That's no surprise. The standard deviation, sigma, is given by the square root of NPQ, where, again, Q is 1 minus P. It's the failure probability per trial. In this case, the probability of a tail. Now, it makes sense that if we want to approximate this binomial NP distribution, then if these conditions apply, if NP and NQ are at least 5, as we said before, then we're going to say that X can be approximated by a normal distribution with these parameters, the same parameters as for the binomial distribution that it's approximating. That makes sense. We're going to use a normal approximation where the mean mu is NP, same as for the binomial, and the standard dev sigma is root NPQ, same as for the binomial. Okay. Now, when we approximate a binomial distribution by a normal, there's another issue. It's the fact that we're approximating a discrete distribution, a binomial, with a continuous distribution, a normal, and that leads to some awkwardness. So to adjust for that awkwardness, we're going to apply continuity corrections. Maybe not later in this course, but for right now, as we're focused on probability, we're going to try to make our estimates more precise. So we're going to apply continuity corrections. Continuity corrections are used to adjust for the fact that we are using a continuous distribution, in this case, a normal distribution, to approximate a discrete distribution, in this case, a binomial distribution. We're using a normal to approximate a binomial, a continuous distribution to approximate a discrete distribution. So a discrete distribution gives us bars in a probability histogram. A continuous distribution gives us these curves, these density curves, and there's going to be some awkwardness. So for example, let's say that we let X be the number of heads when a fair coin is flipped 100 times. let X be the number of heads when a fair coin is flipped 100 times. X will then have this corresponding binomial distribution, where n equals 100, the number of flips or trials, and p equals 1/2. The probability of heads is 1/2, by definition of a fair coin. Now let's say that a friend of ours is going to flip a fair coin 100 times. Well, and I win a bet with my friend if the coin comes up heads between 45 and 55 times inclusive, meaning that I win the bet if my friend gets exactly 45 heads. Also, I win the bet if my friend gets exactly 55 heads, or if my friend gets any number in between, 46, 47, and so forth. I want to find the probability that I win this bet, that the number of heads will be between 45 and 55 inclusive, including these numbers of heads at the boundaries. Now, later on, we're going to find z-scores for boundary values, but I need to nudge these a bit because I want to apply continuity corrections. So here's the idea. We associate the integer value a, such as 45 or 55, in the binomial distribution with the interval of real numbers from a minus 1/2 to a plus 1/2. Basically, these are the real numbers that round off to a when we do our approximating normal distribution, and we're going to think rounding. Let's do some examples of that. In particular, what are the real numbers that round off to 45 to the nearest integer, and what are the real numbers that round off to 55 to the nearest integer? Bottom line. What are the real numbers that correspond to the integer 45 from the discrete binomial distribution? It's this interval of values over here, this range of values over here. What are the real numbers that round off to 45 to the nearest integer? It's the interval from 44.5 to 45.5. To get these goalposts, these fence posts, I take 45, I subtract 1/2 or 0.5 to get the 44.5, and I add 0.5, I add 1/2 to get the 45.5. And that's true for any integer. When we go from the binomial to a normal approximation, I take the integer of interest, I subtract 0.5 for the left fence post, and I add 0.5 for the right fence post. Likewise, for the integer 55 for the binomial distribution, well, what's the interval that corresponds to that? Actually, I'll use blue for this. What real numbers round off to 55? The real numbers from 54.5 to 55.5. Now, I realize that technically 55.5 rounds up to 56, but that's the best we can do. Bottom line, this interval, this block of real numbers in here, will round off to 55, just as this block of real numbers over here will round off to 45. Now, this shaded region inside here corresponds to the values for our normal distribution where I win my bet. Well, of course, I win for 46 heads, 47 heads, and so forth, but I also win for exactly 45 heads, meaning this block, so I shade this in. And I also win for exactly 55 heads, meaning this block, so I shade this in. I win if the coin comes up heads exactly 45 times, or for that matter, exactly 55 times. So I shade in both these boundary blocks, which means where are our actual goalposts when we convert to z-scores? What are the boundaries for this shaded region over here? We go all the way from 44.5 over here. I'll put this in purple, actually. We have to go all the way from 44.5 over here as our left goalpost to 55.5 over here as our right goalpost. And the shaded region that we want is everything in between. Okay, so to approximate the probability that the number of heads is between 45 and 55 heads inclusive, we actually want the probability that corrected x for a normal approximation will be between 44.5 and 55.5. And in fact, at this stage, the bars won't matter because we're dealing with a normal distribution, a continuous distribution. Normals are continuous. Normals are continuous. So we don't care about the bars so much. For discrete distributions like binomials, we can care about the bars. Here we do. But by the time we get to normal, we don't care about the bars anymore. And again, why are we doing this? Why are we performing these continuity corrections? Well, for example, why do we replace the 45 here with the 44.5? Because if we take a z-score for the 45, then what's happening? Well, really, we're supposed to consider this corresponding binomial bar, this binomial bar here, when we consider adding these various probabilities for the binomial. But if you take 45 as your boundary z-score, if we took the z-score for 45 as our boundary, what happens? We're going to cut this boundary bar in half, and we're going to lose this probability mass over here, which means we're going to be a bit off. Now, again, continuity corrections will not bother us later in the semester, but if we want to be as accurate as we can, we want to get this piece of bar, which means that we prefer the 44.5 as our true boundary for the normal as opposed to 45. Likewise, we prefer 55.5 to 55 because we want this extra piece of bar. This extra piece of bar over here, which really is supposed to count. All right, next up, we're going to do an example. And in particular, we're going to find this probability.
Okay, so obviously the example will help, but anything about these foundations before we go to the example? Right, again, keep it in chat. The homework will help, obviously.
Hi, everyone. Let's continue with lesson 23 and do some examples of normal approximations to binomial distributions. Example 1 is our classic coin example. We will flip a fair coin 100 times. Let x equal the number of heads in the 100 flips, so a head is a success. Approximate the probability that we win our bet. Now our bet is that the coin will come up heads between 45 times and 55 times, inclusive. So we win the bet if the coin comes up heads exactly 45 times or exactly 55 times, or anything in between. These bars do matter at this point. Describe the distribution of x. Well, what kind of distribution is it? It's going to be a binomial distribution where n equals 100 trials corresponding to the 100 flips, and p equals 1/2 because we're flipping a fair coin. We're flipping a fair coin, so p is 1/2. This is a discrete distribution, so the bars matter at this stage. In part B, we're going to verify that a normal approximation to this distribution would be appropriate. So we need to verify that NP and NQ will both be at least 5. And by the way, the 5 here does not come from algebra. It comes from practical observation. It's like the n greater than 30 condition from the CLT. Okay, well, NP, n is 100, p is 1/2, n times p is 50, which is way over 5. NQ is 100 times, again, 1/2, because if q is 1/2, if p is 1/2, then q is 1 minus p, or 1 minus 1/2, also 1/2. 100 times 1/2, again, is 50, which is way over 5. If both NP and NQ are way over 5, then we expect the normal approximation to do a very good job, especially with continuity corrections. So our mean here, by the way, is given by NP, which is the same formula as this over here. So when you calculate NP, you're also calculating the formula for the mean, or the expected value of x. It's 50. N times p is 50, which is the expected number of successes or heads. This makes sense because if you're flipping a fair coin 100 times, then the expected number of heads, it makes sense that it's 50. By the way, NQ is also 50. That's the expected number of failures or tails. These are both at least 50. In fact, they're way over 50. So the normal approximation is applicable in this case. C, describe the normal distribution that can be used to approximate the distribution of X. So what is the distribution that we can apply? Well, as I just mentioned, the mean is NP, or 50. Okay, that's the first key parameter for the normal. The mean mu is NP. We work that out. 100 times a half is 50. Technically 50 heads, if you want the unit. The standard deviation, sigma, is given by the formula, the square root of NPQ, which is the square root of 100 times P is 1/2, and Q is also 1/2. It turns out to be a nice integer, 5 heads, standard deviation. Which means, by the way, by the 2SD rule, that we would really expect, with about 95% confidence, that we'll get between 40 and 60 heads if you use the 2SD rule. What about 45 to 55? So we have our parameters here. So therefore, we're saying that X, the number of heads, has a distribution that is approximately normal with mean 50 and standard deviation 5. All right, now let's apply continuity corrections and rewrite this probability expression in terms of corrected X. So we're going to nudge or move these boundary values slightly and take z-scores later on for those new boundary values. But I need to move these slightly in order to apply the continuity corrections. Well, what are the real numbers that round off to 45? And what are the real numbers that round off to 55? The picture looks like this. The real numbers that round off to 45 are the ones between 44.5 and 45.5, as we said in the previous video. The real numbers that round off to 55 are between 54.5 and 55.5. So this block represents the integer 45 from the binomial. This block represents the integer 55 from the binomial. But remember, we win if we get exactly 45 heads, so we do include this block. And we also win if we get exactly 55 heads, so we pick up this block. And we win for anything in between, 46, 47, and so forth. So we want to shade in this entire region here. So ultimately, what are our outer goalposts? Our goalposts are going to be from 44.5 out here to 55.5 out here. These are the true boundary values that'll trap all of the shaded region inside of here. I'll put this in red for emphasis. Again, we want 44.5. We want 44.5 as our left key goalpost, and 55.5 as our rightmost key goalpost. And we ultimately want z-scores for these new boundary values over here. These are corrected values for X. This is to take care of the awkwardness of having a continuous normal distribution approximating a discrete binomial distribution. In part E, find the z-scores for the boundary values for these new corrected values. What are the z-scores for these? 44.5 and 55.5, which traps all the stuff in the middle that I want. And by the way, at this point, the bars no longer matter. So if you want, you could put bars over here, but since we're dealing with a continuous normal distribution, it doesn't matter at this point whether you put bars or not. All right, find the z-scores for these boundary values. Well, for 44.5, the z-score is X, which is 44.5, minus the mean, which is 50 heads, remember, all divided by sigma, which is 5 heads. Remember, it's basically heads divided by heads, right? Heads minus heads is heads. Heads divided by heads, no unit. Z-scores have no units. So Z equals, all in heads, 44.5 minus 50, the mean, all divided by the standard dev, 5. Don't forget to process the numerator before dividing. The result is negative 1.10. And why does it make sense that the Z-score is negative? Because 44.5, the boundary value we're looking at, is less than the mean of 50. So the Z-score is negative. That's a good check. What about 55.5? Well, since these are both symmetric about 50 heads, the mean, you could just use symmetry and say it's positive 1.10, or you can go through the formula again, where you replace 44.5 with 55.5. This time you get a Z-score of positive 1.10. So these are the Z-scores that correspond to the corresponding corrected X scores over here, the boundary scores. In part F, write the corresponding probability expression for Z. So write this here, this expression in terms of corrected X, in terms of Z. Well, instead of 44.5, we have a Z-score of negative 1.10. That's the Z-score for 44.5 heads. Instead of 55.5 heads, we'll convert it to its Z-score, 1.10, positive 1.10. So now we're focused on this probability over here. And we can use the software or tables for Z-scores, for a standard normal. Now, in the stated problem, I give hints. We're going to approximate the probability of me winning the bet using these hints for the Z distribution, the standard normal. We're going to use the probability that the area or probability to the left of positive 1.10 is 0.8643, this big chunk over here. Of course, it's way bigger than 0.5. And then I want this area or probability to the left of negative 1.10, which is smaller, is 0.1357. In fact, by symmetry, you can see that this and this are complements. These add up to 1. Again, that's by symmetry. If this were, for example, 2 or 3, then this symmetry idea wouldn't work. We wouldn't have symmetry. But here we do have symmetry. All right, so I have this big area. I have this small area. This looks like an in-between area or probability. So what do I do with these probabilities? I subtract them. Because what I want is this blue shaded area in the middle. In order to get that, I want the probability or area to the left of positive 1.10. I want the probability or area to the left of negative 1.10. These areas I got from the hints, right? These are the numbers I got from the hints up here, 0.8643 and 0.1357. What do? I subtract them in order, larger minus smaller. It better be larger minus smaller because the result cannot be negative. 0.8643 minus 0.1357 is 0.7286. So according to this method, we have about a 72.86% chance of winning my bet that the number of heads will be between 45 and 55 heads inclusive. Now, software can confirm this for us because software, like Excel, say, can apply this binomial probability formula. I hope this looks familiar from lesson 17 or 18. I think it was lesson 18, actually. Lesson 18. The binomial probability formula, which was optional. You didn't have to memorize it. But this was the probability of getting X successes out of N trials. And you didn't have to memorize that. This was the formula. Well, Excel can apply this formula. So what can Excel do? Excel can work out the probability of getting 45 heads using this formula, the probability of 46 heads, and so on, up to and including the probability of 55 heads. And in fact, I had Excel do that. According to Excel, if you flip a fair coin 100 times, you count the number of heads as successes, you let X be the number of heads, X will have a binomial distribution with N equals 100 trials or flips. We assume a fair coin. P, the probability of heads, is 1/2. And here we have the probability distribution table. you can see the probability of 0 heads is close to 0. This is using scientific notation. This is about 8 times 10 to the negative 31st. It's basically 0, just a little bit above 0. In fact, it's very close to 0 for these values of x. But then we start to register really, especially in the 30s or so, numbers of heads. And this is what we want. Here's P of 45, which we include. It's about 5%. Here's P of 55, which we include. It's about 5%. Notice that even the most likely number of heads, 50 heads, is not even 8%. Remember that total probability is 1 and is being split up among all these different possibilities. And even the probability of 50 heads, the most likely number of heads, is not even 8%. You would not want to bet the farm or your house on a particular value of x, although P of 50 is the highest. So what happens when you add up all these probabilities? I had Excel do that by using the sum operator. It turns out to be this. To 8 sig figs, or decimal places, 0.72874698. Okay, which was basically what I gave you over here. The actual probability to 6 decimal places is 0.728747, which is basically what Excel is saying, 0.728747 to 6 decimal places. This is essentially exact since we're using the binomial formula. It's the correct probability to 6 decimal places. And it's pretty darn accurate. So our answer of 0.7286 was pretty good. That was the answer that we got, even to 4 decimal places. It was 0.7286, and that was pretty good. To 4 decimal places, the quote-unquote exact answer is 0.7287, up to rounding error. So the error here is due to rounding error. 0.7286, what we got from our normal approximation with continuity corrections, very good. Now, if we had not applied the continuity corrections, we would have been pretty close, 0.6826. That sounds a bit familiar because we were talking about within about 1 standard deviation of the mean. So it's not so surprising that this is about 68%. But you can see that the 0.7286 is a fair bit more accurate. Although later on in the course, we're not going to bother with continuity corrections, and we may have to be satisfied with something like that. Actually, the 0.7286 is for 1.10 standard deviations. 0.6826, hey, if you had not applied continuity corrections, if you had taken z-scores for 45 and 55, you would have gotten z-scores of -1 and +1. And actually, this is the probability of being within 1 standard deviation of the mean. So yeah, we would have gotten z-scores of 1 and -1 had we not applied continuity corrections. This is what we would have gotten. Actually, the better z-scores would have been 1.10 and -1.10. So this was actually a bit more accurate. We get a bit more probability. Because remember, if we had just used 45 and 55, we'd be losing these pieces that are getting cut off if we had not used the continuity corrections. All right. Now, what about other wordings? What if we wanted the probability, in example 2, what if we wanted the probability of at most 45 heads? Does at most 45 include 45? Yes, it does. It includes 45 heads. And do we go left or right? Do we want lesser values or greater values? We want lesser values. So we want 45 and we want lesser values. Remember, what are the real numbers that correspond to 45 for the normal approximation? Between 44.5 and 45.5. Do we want 45 heads? Yes, we do. So we do shade this piece and also everything to the left. We want all lesser pieces as well, which means the true goalpost we want is at 45.5. The goalpost I want, there's only one because there's only one boundary value. I want the goalpost at 45.5, not 44.5, because I want all the shading to the left of this goalpost. So the probability that x is at most 45 heads is about the probability that corrected x is less than 45.5 heads. Again, I don't care if you put the bar here or not at the normal stage. At the normal stage, I don't care. What about part B, the probability of getting more than 55 heads? Does more than 55 include 55? No, it does not. More than 55 heads excludes 55 heads. And which way do we go? Left or right? Lesser values or greater values? We want greater values. But we do not include the 55 itself. We do not want the 55 itself. Now, the real numbers that round up to 55, what are they? The real numbers between 54.5 and 55.5. But wait a minute. Do I win if the coin comes up heads exactly 55 times? The answer is no. I don't want this block from 54.5 to 55.5, but I want to shade everything to the right of that block. So what's the true goalpost or boundary value I want for corrected x? In purple, I want this guy, 55.5. The probability that x is greater than 55 heads or more than 55 heads, it's about the probability that corrected x is greater than or more than 55.5 heads. Because this here is the true goalpost, 55.5, not 54.5. Again, there's only one boundary value. You only have to find one z-score, and you want a right-tail probability. Some final comments at the end.
Okay, so any questions? That's sufficient for the homework, but any questions? I want to wrap things up here.
Hi, everyone. Just a few final comments about lesson 23. We were talking about binomial distributions. For example, flipping a fair coin 100 times. Well, what is the most likely number of heads? The most likely number of heads for a fair coin? If flipped 100 times, 50. The probability of 50 heads was about 8%, and that was the highest probability, even though you probably wouldn't bet your life on it. Now, you might find that rather curious that the probability of 50 heads is not that high. We'll notice that the total probability of 1 is being spread out in around these middle values of x. You can see how the probabilities are declining rather slowly around here. The probability of 51 heads or 49 heads, they're about equal to p of 50. And then we do get a serious dropping off down here. Even when we get one standard deviation away, we get a pretty serious dropping off in the black zone over here as opposed to the red zone. Now, the probability of 50 heads wasn't even that likely. What about the probability of getting exactly 500 heads out of 1,000 flips? The probability of getting exactly half heads out of 1,000 flips. That's even smaller. It's about 2.5%. What about the probability of getting exactly 5,000 heads out of 10,000 flips of a fair coin? That's going to be even less likely, not even 1%. So, and by the way, I'm assuming that n is even. If n is odd, the probability of getting exactly half heads is 0. But let's assume n is even. If you let n approach infinity, that means that the probability of getting exactly half heads is approaching 0. And then it kind of makes more sense how in a continuous distribution, the probability of getting a particular number is 0. Because take a look here. If you consider n approaching infinity, this probability is approaching 0. It's a very similar idea. If n approaches if n is 1,000,000 or 1,000,000,000 or 1,000,000,000,000, then this becomes very, very close to 0. So then you can see how probabilities can be 0 in continuous distributions. A second comment. Why do these normal approximations work for binomial distributions? It comes down to the central limit theorem for sums. So for example, let's say that x is the number of heads on 100 independent flips of a fair coin. I forgot to mention fair coin. P equals 1/2. Then X can be considered to be the sum of 100 indicator variables. For example, X sub 1 is 1 if the first flip is a head, it's 0 if the first flip is a tail. It's kind of like Christmas lights. Are they on or off? X sub 2, it's 1 if the second flip is a head, it's a 0 if the second flip is a tail. So each of these lights, each of these 100 binary indicator variables is a 1 if it's on, a success, a head. It's a 0 if it's off, a tail. X counts successes, the heads, the lights that are on. Well, 100 is big, it's more than 30, right? We start with a uniform distribution that's at least symmetric, and the CLT likes symmetric distributions. We're considering a sum of 100 IID, independent and identically distributed random variables from a symmetric distribution. The sum is about normal, according to the CLT for sums. So this connects together with the topic of the CLT from the previous lesson. It all ties together. Take care.
Yeah. So, yeah, I don't know if you think that's cool. I think it's really cool that it ties together. Why is it that we see normal approximations, not just in real life, but in sums, averages, and to approximate these binomials? That's why we see normals in so many applications. That is it. It was a lot. That's one of the toughest days we have this semester. But we finished part 3. I will stay for questions. All right. Otherwise, have a great weekend. And I will get your first homework graded by next week because the withdrawal deadline is Friday of next week. So I really better get something graded by then. All right. Any questions? I will stay for questions. Yeah, it was a lot. It was a lot. And we can do a bit today. Let's see. Okay, I can answer a few questions here. Okay, and I'm still recording. Let me know if you'd like me to pause it. Okay, so let's go to 22. I can at least offer a few hints or a few bits here. Okay, so 22. Yeah, because I want to give people a chance to work on these, but let me see if I can give a little hint here. Let's see, 2B. Okay, finding the ST for X bar. Oh, yeah, the standard error, right. So remember, the formula for standard error. Okay, so this is the standard error of the mean, the standard deviation of the X bar distribution, that's given by the CLT, sigma over the square root of n. So that's going to be my key hint to you. I would like people to take some time, review the lesson, work that out. But to answer your question directly, the standard error is given by sigma over root n. And you're going to use that in part B because we want to analyze averages. Yeah, so if the sample size is 4, that's okay. And remember, it's okay for the sample size to be small, but take a look. In the problem, I say the scores are approximately what? Normally distributed. So regardless of the sample size, you're allowed to use the CLT. Remember, if you start with a normal, it's okay if n is less than 30. So that's the key. Right. Now, of course, the sample size matters in terms of your results, but in terms of your right to use the CLT, if you start off normal, you have the right to use the CLT even for n equals 1. In fact, for n equals 1, there's no issue. You just get sigma. Yes. So it's good to watch the assumptions, but it's good that you were checking, right? Because if I had not put that there, then you're right. We couldn't apply the CLT if I did not have that. 23A. Right. Okay. So here, it's kind of similar to what we did in lesson 18, which is it's one of these multiple choice test problems, right? You're guessing randomly on an ABC multiple choice test with 60 questions. X is the number of questions the student gets correct.
Yeah.
Yeah. X will have
Yeah, I was sorry. I did X, the little squiggly bin,
Mhm.
and then N equals to 60. So
Right.
is the P equals to 1/2 or 30?
Careful. So let's say
Oh,
that
okay.
you have a question and it has options A, B, and C. Only one
Yeah.
is correct. You're guessing randomly. What is the
Okay.
probability that you get that question correct by pure chance?
3.
1/3.
Uh,
Right. There are three. Uh,
sorry.
okay. So, okay. Okay. So there are three options. You're guessing randomly. Only one of the three is correct. Uh, the probability you get the question right by just pure chance is one
Yeah.
third. Right. So part A, I just asked you to do that. There's no way I'd have you
Oh,
write out the table because you want Excel to do that. I mean, that thing has 61 rows. There's no way I'd want you to do the table. That's insane. But but at least describing what this is. And then the goal is that we're going to use a normal approximation so that you don't have to go through Excel.
okay.
Although I know that for some students they'd rather use Excel, but the idea is that you don't need Excel in order to work this out, assuming you have basic statistical tables. You know, yeah, to get the hints here, right?
Yes, got it. Thank you.
You're welcome. Yes. All right. Any further questions? And remember, next week we'll have lots of time to discuss the questions. On Monday, it'll be more detailed. I can discuss the questions in context, right? And then Wednesday's a rush. So you want to try to get your homework basically done by Monday night after a Monday class. So Monday we'll be reviewing the ideas more carefully as you ask questions. I do welcome questions now, though. If you have questions now, we are entering a long weekend, so of course you'd like to get some work done. Any questions regarding the particulars here?
Yes, Professor. I get a question of lesson 22. Also the problem of number two, the part A. I want to check the answer if is
Oh,
common five,
yes, I do
common five,
have.
six, one.
Yeah, I do have the answer, and I don't mind showing that because you have to show work anyway, right? So let me.
Yeah.
So on the answer to A on
Uh-huh.
two, you mean 2A?
Yeah,
Yeah.
2A.
Okay. For 2A, the answer is for okay, and I checked this with my previous classes. Um, 0.1587.
Common five is 7. I get like common five 69. Oh,
Right, but remember, it's
oh,
going to be the
I get it.
right.
I get it.
It's the complement of this.
Yeah,
I think it's this right tail here, right? It's the
yeah,
complement of this.
I
So you
get
want
it.
one minus that.
I copied down the wrong number.
Oh, okay, I see. You're
Yeah, thank you.
welcome. Yes, yes. And remember, use the hints to your benefit. So you don't have to
Yeah,
use Excel, right? Although it's nice to know you can do this on your own without my hints. But yeah, you could use Excel or Tutor Homework. But I give you the hints.
yeah, I just used the formula of the X bar. Yeah,
Oh
yeah,
yes, yes. Here is just one student. Right. Okay.
okay, thank you.
Oh, you're welcome. Yes. Anything else? Anything else? Wow, you folks are on it. Yeah, you're doing the homework on time. That's really good. Any questions? Any questions? It's 9:44. I'll pause 1 minute as you gather thoughts. So 9:45. All right. I'll give you a minute to kind of gather your thoughts. Okay, it's 9:45. Does anyone have any questions, or do you think you might have a questions in the next like 3 to 5 minutes? Any questions? Any questions? All right. Well, have a great weekend, all of you, and I'll see you all next week. Take care.